Alright, so this is my video on waves. We covered the first 5 pages of your waves packet in class on Friday. If you were not there, I have posted the key to those pages. There are also all sorts of videos out there that you can watch. One of your classmates recently discovered the flipping physics videos, which are good. There's a couple of others really good ones out there that I'll try to post links to. I'm not going to go back and video that part. We're picking up the bottom of page 5 where it talks about superposition and interference. So waves don't behave like other objects. They don't stick together the way that, wow, why are we experiencing such extreme lag with the camera today? Alright, I'm going to keep going and we'll see if that ends up being a problem. It's kind of looking like a problem. If you hear weird noises in the background, this is my first time recording at home, and I have 2 dogs, and I've tried to occupy them, but they're still in existence. Anyway, when waves collide, they don't bounce off each other or stick to each other or do any of the things that normal things do, where we can talk about, you know, conservation of momentum or conservation of energy and like look at equations to figure out how they act. Instead, the waves interfere with one another. They briefly become one wave, and it's just for that moment, because then they just keep moving. They keep doing whatever they were doing before. There are 2 main types of interference. The first, and their opposites, there's constructive and destructive. So for constructive, it's when the crest of one wave overlaps the crest of another so that they line up, and the result is that they become one larger wave. So at the top of page 6, we have an example. We have 2 waves that are headed towards each other, crest to crest. 2 wave pulses on a string are moving towards each other. They're going to interfere constructively since their amplitudes are on the same side of the string's resting position. Draw what the waves will look like when their pulses meet. So this is the height of one wave, and we're doubling that. So what you should draw is something about like this, except not lopsided, because that's just my inability to be not lopsided. It would be about double the height of the original, but the same width, because just their amplitudes add together. Their wavelengths don't add together. The big thing to remember, though, is then they're going to just keep going. This is like, let's say we had labeled these up here. This was like 1 and this was 2. Down here, this is wave 2, which is continuing to move on its way. And this is wave 1, which is continuing to move on its way. They only interfere for the specific time when they're in the same place. Alright, so the opposite of that is destructive interference, which is exactly what it sounds like it would be. So you have the crest of one wave overlapping the trough of another, so they're not lined up. Down here we have a picture, 2 wave pulses. They are going to interfere destructively. Draw it in the second picture below. So basically you're adding them together. For up here, for constructive, we had a positive amplitude and a positive amplitude, so we got 2 times that positive amplitude in our final drawing. Down here, on the other hand, we have a positive amplitude and a smaller negative amplitude. So if this is like, I don't know, positive 3, this is negative 1, then the result is going to be like positive 2. It's still going to be above the center line because that one was larger, but it's going to be smaller than the original one was. But that's only true for that moment when they are in the same location. Afterwards, our positive 3 is on here going on its way, and our negative 1 is over here continuing on its merry way. There's something this packet doesn't mention that I don't know if it's a term you'll see, but seems like it's worth mentioning, which is total destructive interference, which is exactly what it sounds like. It's when you have two waves of exactly the same size that end up interfering. So they're like this. And the result when they meet is that there's no wave. For that particular moment, there's no wave, which is why it's called total destructive interference. Once we're back over here, you would have your two waves back again. This is actually how noise-canceling headphones work. They create waves that have total destructive interference with the outside noise. So that's kind of cool. Yeah, it's worth noting that while these definitions specifically talked about crests and troughs, and as we learned in class, only one of the two types of mechanical waves actually has crests and troughs. The other has compressions and rarefactions. It's the same principle. They also, sound waves, which are longitudinal, also interfere constructively and destructively. All right. There was at least one question on the multiple choice part of the practice test from last week that was about interference, and it showed a bunch of pictures and was like, what is this going to look like during the collision? What's it going to look like after the collision? All right, page 7 talks about standing waves. A standing wave is a wave that by definition appears to stay in one place. In some positions, the string vibrates with a large amplitude. These are called antinodes. In other positions, the strings don't vibrate at all. These are called nodes. Oh, you can't see the words I'm writing. The lag is so bad that it's not in real time. Anyway, I don't know, I guess my home internet is struggling more than the school's internet, which is hard to believe because the school's internet is not always great. I don't know why I'm having more trouble than usual. So the reason that standing waves exist, wow dog. The reason standing waves exist revolves around interference. Waves are traveling back and forth along the string, reflecting off each end and interfering with each other in the middle. That's, if you remember when we played with the slinky in class and we would send the slinky down, it would come back and go back and forth. So they're actually interfering with in each other during that whole thing. So the interference causes constructive interference in some places, which results in your antinodes, and it causes destructive, total destructive interference in other places, which is where you get nodes. So if you pluck a string, this example is a guitar string of 1 meter, you produce a standing wave of the longest possible wavelength and thus the smallest possible frequency. The string will look like the preceding picture if you watch it carefully. The wavelength of a standing wave is always twice the node-to-node distance, and that's because think of drawing a full wave. So a full wave, a wavelength, is from the beginning of the wave to the end of the wave. So that's the full wavelength. But we don't have that. We just have this first hump. So it's half the wavelength. Wavelength is lambda, so this would be like lambda over 2 here in this picture. So in the picture above, when we have a guitar strength of 1 meter, the node-to-node distance is 1 meter. The wavelength here would be 2 meters. But what if you press your finger lightly on the middle of the string, forcing a node to exist there? Then you create a harmonic, like the one shown in the following figure. Now the wavelength of this standing wave is a full meter, because we're seeing one full. So again here, wow, I don't know. Okay, we are live, we're just lagging. So here you see the whole wave. in the picture, so that length of 1 meter is lambda. But that's because now the node-to-node distance is only half a meter. So lambda is still 2 times the node-to-node distance. And you can have any number of antinodes on a string. So in this case, the node-to-node distance would be like 0.33 meters. So the wavelength of this wave would be like 0.67 meters or something. So, fact, for a string fixed at both ends, or for a pipe open at both ends, the smallest frequency of a standing wave is given by F1 equals V over 2L. You can't see what I'm doing. All right, let me go ahead and just start out by saying that this is not on the formula sheet. And it is something that they expect you to be able to use. There was, I think it was actually a pipe, which we're going to look at in a second. But there was definitely something about the frequency of a standing wave on the practice test. Now, this is not something you need to memorize. The answer is almost never memorize. They give you exactly one equation for waves specifically. They give you those periods of pendulums and springs that we talked about in class, but they don't even lump those with waves for whatever reason, because they're technically simple harmonic motion, which is similar to waves, but not a wave. The only formula they give you is a version of V equals lambda F. I think it's phrased as lambda equals V over F, maybe. This is just a version of that, because if you rearrange this formula for F, you get F equals V over wavelength. And we just said that for a string that's fixed at both ends, lambda equals 2 times the length of the string. You just plug that in, now you have this formula. And then you don't even need to memorize that, because if you just think about it, if you think, okay, a string is fixed at both ends, it creates this wave, okay, that's only half a wave, so we need to multiply by 2 to get that full wave. Other harmonic frequencies for this string must be whole number multiples of this fundamental frequency. If you're dealing with a pipe instead of a string, the speed V is usually the speed in air, which is about 300, speed of sound in air, which is about 340 meters per second. For a string, it's going to depend on the tension in the string, and the mass of the string, but you're usually talking about a few hundred meters per second. So if a guitar string can produce a fundamental frequency of 100 hertz, then harmonics that can be played are 200 hertz, 300 hertz, 400 hertz, etc. It cannot play frequencies of like 150 hertz or 370 hertz, because remember, all you're doing to create different harmonics is pressing that in specific places. And yes, this is not a whole number, but that's because don't worry about it. I was solving for wavelength. We actually talked about this in class, but when you're talking about music, people use terms like pitch and loudness. Those relate directly to sound terminology in that pitch is frequency and loudness is amplitude. So a guitar can generally play any note and not just harmonics of the fundamental frequency. This is because you don't actually play guitar just by depending on that one harmonic or harmonics of that fundamental frequency. Rather, you use the frets to change the length of the string. Since the speed of the waves on the string is unchanged, shortening the string, or the L, changes the frequency. The fundamental frequency of the shorter string will be higher, and thus, as you make the string shorter and shorter by moving up the neck of a guitar, you get higher and higher pitched notes. You can also tune the guitar strings by tightening and loosening the strings. A tighter string will produce a higher wave speed. For the same length of string, and thus the same wavelength, if you have a higher speed and the same wavelength, higher speed, same wavelength, you're going to have a higher frequency note. A higher frequency note means a higher pitched. So the tighter you make a guitar string, the higher pitched note you're going to get out of it. Now, this was all for if you have something where you have a node at both ends, a string that's held at both ends. But for a lot of instruments that depend on vibrating air columns, you have one closed end and one opened end. In this case, you're going to have a node at one end, and you're actually going to have an antinode at the other end. Antinode. In this case, the wave with the longest possible wavelength is shown in the preceding figure. The wavelength of the standing wave is always twice the node-to-node distance, but here the wavelength is so long we don't even see the second node. It turns out that the wavelength for this pipe, the whole pipe was 1 meter, the wavelength is going to be 4, or 4 times the length of the pipe. The way to think about this is, again, not to memorize anything, it's just to think about drawing out a wave. That's one full wave, so that whole distance is our wavelength. But then look at how that matches up with this picture. We've only got this first chunk of the wave from the node to the first antinode. If you chunked out the rest of the wave, you'll see that what we have is only 1/4 of the whole wave. So that's why it's 4 times longer. That leads us to, again, have a formula that's not on the, that's not the right page. There was a fire truck. We're not there yet. This again leads us to a frequency that's not on the formula sheet. For a pipe closed at one end or a string that's fixed on one end but free at the other, the smallest frequency of a standing wave is given by V over 4L, where L is the length of the pipe or the string. And again, this isn't on the formula sheet because it's just a way of rewriting V equals lambda F, F equals V over lambda, and here lambda is 4L. You don't need to, you couldn't see any of that. You don't need to memorize that. You just need to be able to sketch that picture that I just did. Now, when you're talking about a pipe that's opened at one end, other harmonic frequencies for the string or pipe are odd multiples of the fundamental frequency. The speed of sound for waves in a pipe is going to be about the speed of sound in air, 340. The fundamental frequency is 85. The other frequencies this pipe can produce are only odd multiples of 85. So 85 times 2 is not 1, but 85 times 3 is 1. 85 times 4 is not 1. 85 times 5 is 1. And that just goes back to, it has to do with fitting this whole wave in. the fact that we're now dealing with only a fourth of a wave instead of half of a wave. That's something you do maybe kind of just need to file away in your mind. So, moving along from the frequencies, there was definitely also a question that was related to this somehow. They give you a table or a graph that you could get like period or frequency from, and then you had to be able to get from that to wavelength. And you had to know how to deal with it. Told you, I think it was an open pipe, but you had to know that relationship. So this does come up. Beats. Beats are something that I'm going to do a really poor job of explaining just in words. I'm going to post, when I post this video, I'll post a link to a site that lets you actually create beats, and that's going to make it make a whole lot more sense, but I will, give it my best shot. Might as well. Beats occur when you play two notes of unequal but close frequencies. Unequal but close. So this doesn't happen when you play two notes that are wildly different. This happens when you play two notes that are like 3 or 5 hertz apart. If you have a couple of tuning forks that are similar but not identical to play, or if you have a tone generator, which is what I'm going to post a link to, you might enjoy generating some beats of your own. There is this very distinctive, I'm not going to try to make the sound with my mouth. There's a very distinctive sound that occurs. And it's due to interference, because when it's constructively interfering, it gets louder, and when it's destructively interfering, it's getting quieter. The frequency of the distinct noise you hear is the difference between the two frequencies you're generating. So if they're off by 2, then the frequency of your beat is 2. Again, that's just something that might come up. I'll post something so that you can actually hear it. It's kind of interesting. Fun facts. The Doppler effect is also something where I'm going to probably post some other links, because there's only so much I can do by talking about it. I have to say, I'm super excited that you don't have to do the math for Doppler effect, which is unusual for me because I like math, but the Doppler effect formula is a hot mess. But you don't have to do the math for it at all. You just need to know what it is and what it would potentially do. You've experienced the Doppler effect. The Doppler effect is the apparent change in a wave's frequency that you observe whenever the source of the wave is moving towards or away from you. It's actually even less specific than that. One of the things I'll probably post is a clip from The Big Bang Theory, which I also am not usually a big fan of, but occasionally they get things right, where Sheldon defines the Doppler effect like 5 times in one episode. It's the apparent change in frequency due to the relative motion between you and the source of the wave. So it can actually be either of you that's moving. It can be you are moving towards or away from something that's making a wave. It can be the wave is moving towards or away from you. It can be a combination of both. The best example is hearing a siren. You're standing somewhere and a siren is moving towards you. As the fire truck, in this case, moves towards you, it's emitting sound waves. So let's say the siren emits one wave when the truck is 50 meters away from you. It then emits another pulse when the truck is 49.99 meters away from you, and so on. Because the truck keeps moving towards you as it emits sound waves, it appears that the waves are getting scrunched together. Then, once it's moving away from you, it appears that the waves are getting further apart. Now imagine that you could record the instant that each sound wave hits you. When the truck is moving towards you, you would observe that the time between one wave and the next is very small. So in this case, the time is getting smaller and smaller. However, when the truck is moving away from you, you would have to wait a while between each one. In other words, when the truck is moving towards you, you register the sirens are making a higher frequency noise. It sounds like the siren is increasing in pitch, and when it starts moving away from you, it sounds like that it is making a lower frequency noise or decreasing in pitch. That's all you really need to know for the Doppler effect, is that as things are getting closer together, and again, it can actually be either one that's moving. As they're getting closer together, you're going to hear a higher pitch noise. As you're moving further apart, you're going to hear a lower pitch noise. A thing to keep in mind, though, is that the effect is rather small. Obviously, it's noticeable. You hear it every time a siren passes you on the highway. But at normal speeds, the frequency of, say, a 200 hertz note will only change by a few tens of hertz, not hundreds of hertz. It's not going to, hundreds of hertz would be a drastically different sound. It would go from like, a low pitch sound to a high pitch sound or something. That's not what happens. It increases enough for you to hear it, but it's not some hugely dramatic change. So that's actually the end of waves. There are a bunch of practice problems that I encourage you to work. I will post Greg Jacobs' answers, and then I might end up posting my own answers. I don't know whether that will be useful or not. Again, I'm going to post some other resources for you. I know some of you freaked out when you saw how much was about waves on the practice test, but the reason I wasn't too worried is because there's just not that much. They apparently like asking about it, but it's the same few concepts over and over. All right.